Right now, inside this entirely unremarkable little metal cylinder, there is a violent microscopic battle taking place.
Yeah, and if that cylinder loses the battle, I mean, the modern manufacturing world literally grinds to a halt.
It's wild. Okay, let's unpack this because today we are cracking open a profoundly detailed 50-page technical document.
Right, the official user manual for Sullair's SXT, SXCS, SXF, and SXH threaded coalescing filters.
And it is a dense read.
Oh, absolutely. But it's a phenomenal piece of engineering literature because, well, it forces you to confront the sheer violence of industrial processes.
Yeah.
We always associate infrastructure with massive, visible things, bridges, dams, giant steel beams.
Right, the big stuff.
Exactly. But the most critical infrastructure often operates entirely out of sight, just managing extreme physical forces on a microscopic scale.
And I know what you, the listener, might be thinking right now.
Oh.
I don't install industrial compressors for a living, so why on earth do I care about a threaded filter manual?
Fair question.
You care. Because understanding this specific technology is, it's basically like acquiring X-ray vision into the high-stakes systems that keep the world around you safe.
Yeah, every automated assembly line, every robotic packaging plant.
Even pharmaceutical clean rooms. They all rely heavily on compressed air. And looking at the manual, the core mission of the Sullair filter is essentially acting as a life support system for all that downstream pneumatic machinery.
Right, because it's designed to process what they specifically call fluid group 2 compressed air.
Fluid group 2, which sounds harmless enough.
It really does, but that classification is critical. When people hear compressed air, they usually just picture concentrated wind.
It's just a really strong breeze.
Exactly. But in an industrial setting, compressed air is a highly aggressive, deeply contaminated slurry.
Yeah, the manual paints a gross picture.
It's awful. You are dealing with intense heat, massive pressure, vaporized synthetic compressor oil, unburnt hydrocarbons.
And suspended water aerosols.
Right, plus microscopic solid particulates like pipe scale and rust.
And if that wet, corrosive mixture makes its way into the incredibly sensitive pneumatic valves of, say, an assembly line robot.
It acts like sandpaper and acid. It will completely corrode, seize, and destroy the machinery from the inside out.
So the obvious goal is purification. But this isn't just about putting a simple mesh screen inside a pipe.
Not at all.
Before we even look at the extreme life and death safety warnings detailed later in this manual, and they are intense, we have to look at the underlying physics.
Because the way this filter separates that toxic slurry from the air completely defies how we normally think about filtration.
Right, because our baseline understanding of a filter is usually like a sieve or a coffee filter.
Yeah, a surface phenomenon. You pour a mixture through a porous barrier, the large particles get trapped on the top, and the clean fluid passes through the holes.
But coalescing filtration, which is what these Sullair units use, that operates on an entirely different mechanism.
It's known as depth filtration.
And the manual breaks down the scale of this defense into 3 distinct filter elements, right?
Yeah, you have the CS, or coarse filter, catching particles between 2 and 5 micrometers.
Okay.
Then the F, the fine filter, which grabs particulates from 0.5 down to 1 micrometer.
You're really small.
And finally, you have the H, the microfilter. This one captures particles between 0.1 and 0.3 micrometers, achieving a 99.99% separation rate.
Which is just staggering. I mean, for context, a single human hair is about 70 micrometers wide.
Right.
We're talking about intercepting dust and vaporized oil aerosols that are essentially ghosts.
And you absolutely cannot achieve that level of microscopic separation using standard paper or synthetic cloth.
Especially not when it's subjected to industrial air pressure.
Exactly. The manual specifies that the primary filter medium is constructed from a matrix of borosilicate fibers.
Borosilicate glass.
Yeah. And the engineering choice behind that is fascinating. If you use standard polymer fibers, the extreme heat of the compressed air combined with the chemical makeup of synthetic compressor oils,
It would just destroy it.
it would cause the plastic to deform, melt, or literally just dissolve. Borosilicate glass provides absolute chemical inertness and structural stability under brutal conditions.
And they anchor that glass matrix using a specialized polyurethane potting compound, right?
Yes.
And then they reinforce the entire cylindrical structure inside and out with a supporting body made of stainless steel expanded metal.
Which is necessary for the next part.
Right, which brings up the most counterintuitive part of the whole design, the airflow. The manual indicates the flow travels from the inside of the cylinder to the outside?
Yeah, the dirty compressed air shoots into the hollow center core of the filter cartridge.
And then violently pushes its way outward through the thick walls of the borosilicate glass. It's like blowing up a balloon that sweats out the bad stuff.
That is a perfect way to visualize it. And what's fascinating here is what that word coalescing actually means in practice.
Right, to bring things together.
Exactly. Because this system relies on coalescing principles, it's not just catching dirt like a net. It is actively forcing a chaotic, high-speed collision of aerosols.
Wow.
As the compressed air pushes outward, the microscopic droplets of water and oil attempt to navigate the incredibly dense, randomized labyrinth of those glass fibers.
So it's less like a coffee filter and more like driving a car through a dense microscopic forest at hurricane speeds.
Yes, the tiny liquid droplets can't smoothly navigate around the trees or, in this case, the glass fibers.
They crash into the trunks.
They lose momentum, and then the air behind them forces other microscopic droplets to crash into them. They merge. They coalesce into massive drops.
And that physical merging is the entire secret to the technology, isn't it?
It really is. The borosilicate matrix intentionally creates fluid dynamic chaos. It forces these ultrafine vapor-like aerosols to collide and combine.
Until they form a liquid droplet large enough and heavy enough that the moving air can no longer carry it.
Right. And at that exact moment, gravity takes over. The heavy, newly formed droplets of oil and water physically slide down the outside of the stainless steel element and drip into the bottom of the housing.
Okay, so you've effectively engineered a way to turn a high-speed, invisible mist into a manageable physical puddle of liquid.
Exactly.
But that success introduces an immediate mechanical nightmare.
Oh, a huge one.
Because you use gravity to pull the liquid out, you now have a puddle of highly toxic, oily water sitting at the very bottom of a sealed vessel that is under immense industrial pressure.
Yeah.
So how does the system physically spit that dirty water out into a waistline without accidentally blasting all the valuable pressurized air out with it?
It requires a brilliant application of mechanical physics. The manual outlines a component housed at the base of the unit called the float drain.
It operates entirely on buoyancy, right?
Yes. Inside this lower chamber is a lightweight float body. As the extracted condensate, that oily puddle, slowly rises in the bottom of the container, it physically lifts the float.
Simple enough.
Right. And once the fluid level pushes the float to a specific engineered height, the upward buoyant force opens a mechanical drainage channel.
And then the immense pressure of the air sitting on top of the liquid just violently forces the water out through the channel.
Exactly.
But the timing of that valve closing has to be absolute perfection. If the drainage channel stays open, even a fraction of a second too long after the water's pushed out,
You've just created an open vent blasting expensive compressed air directly into the factory.
which is loud and incredibly dangerous.
Right. So the manual specifies a very specific design constraint to prevent that. The float mechanism is calibrated to close the drainage channel well before all the liquid is expelled.
Okay, so the system never drains itself completely dry during normal operation.
Never. It intentionally leaves a calculated volume of liquid pooling in the bottom of the container.
So that leftover liquid essentially acts as a physical plug.
It creates a permanent liquid seal. The pressurized air physically cannot escape because there is always an impenetrable barrier of heavy water sitting between the air mass and the open drain channel.
That's so clever.
And the manual also notes that for facilities dealing with massive volumes of condensate, this internal float drain can be swapped for an external system.
Right, the Solimax steam trap system.
Yeah, which handles larger liquid loads electronically.
I do want to dig into a specific mechanical detail about that float drain, though, because looking at the manual schematic, there seems to be a deliberate engineering paradox.
Oh, the depressurization state.
Yes, the documentation emphasizes that the drain operates in a normally open or NO configuration when the system is depressurized.
Right.
It specifies that the drain valve mechanically springs open whenever the operating pressure drops to 7.25 psi or lower. Wait, if it's naturally open when there's low pressure, doesn't that mean the system just actively leaks when you turn it off?
It seems like a flaw until you view it through the lens of worst-case scenario engineering. If we connect this to the bigger picture, having the system default to an open state when depressurized is a non-negotiable mechanical failsafe.
Walk me through that.
Consider the environment. A manufacturing plant shuts down its main compressors on a Friday night. The air pressure in the miles of piping slowly bleeds off and drops.
Sure.
As the pressure inside our Sullair filter falls below that 7.25 psi threshold, the drain mechanically forces itself open, dumping whatever condensate is left into the waistline.
Which purges the system. Because if it defaulted to a closed position without pressure, that leftover water plug would just sit there in the dark.
Exactly. And stagnant, highly acidic compressor condensate pooling inside an aluminum housing for 48 hours will aggressively accelerate corrosion.
Oh, wow.
Even worse, if the ambient temperature of the facility drops below freezing over the weekend, that trapped puddle of water will turn to ice, expand, and physically crack the expensive aluminum housing from the inside.
So by failing in the open position, the engineers guarantee the housing inherently purges itself.
Right. It remains completely dry and safe when the system is offline.
And this concept of engineering against catastrophic failure leads us directly into what I found to be the most sobering section of this entire 50-page document.
The safety warnings.
Yes, because the more you read, the more you realize you are not dealing with a simple plumbing fixture. The extreme safety warnings detailed here recontextualize this unassuming metal cylinder into a literal live hazard.
The physical forces involved are just staggering. In the technical data section, the manual lists the maximum operating pressure for the majority of these threaded filter models at 232 psi.
That is massive.
It is. To ensure structural integrity, they perform rigorous load tests, subjecting the housings to 10,000 rapid pressurization cycles at that maximum threshold.
232 psi. I mean, to put that into a relatable perspective, the tires on your car are typically inflated to around 32 psi.
Right.
This aluminum housing is holding back more than 7 times that amount of explosive energy. Constantly.
And the manual does not mince words regarding this threat. Under the danger headings, it explicitly warns of death or severe injuries.
Resulting from, quote, fast or sudden exiting compressed air or due to bursting system parts.
The physics of explosive decompression at 232 psi are terrifying. If the integrity of that aluminum housing were compromised,
or if an untrained technician attempted to unscrew the casing while it was still under active pressure,
the latent kinetic energy would instantly release. The metal components of the filter would accelerate outward at lethal velocities, effectively becoming shrapnel.
which entirely justifies the extreme personal protective equipment, or PPE, protocols.
Oh, absolutely.
I mean, to simply perform basic scheduled maintenance on this filter, just changing the internal glass cartridge, the manual mandates, an FFP3 respirator,
Liquid-resistant protective gloves.
industrial safety shoes,
Safety glasses with side protection.
a heavy-duty hearing protection. You're outfitting yourself like you're walking into a biological hazard zone just to turn a wrench.
Well, it addresses a twofold occupational hazard. First is the acoustic trauma. Even a controlled sudden release of compressed air at 232 psi generates a shockwave of sound that can cause instantaneous permanent hearing damage.
Makes sense. And the second hazard.
Chemical and biological. We discussed that the condensate inside isn't just water. It is a highly concentrated, toxic slurry of vaporized synthetic oils, microscopic shards of metal from the compressor turbines, and aggressive bacterial colonies.
Bacteria that thrive in the dark, warm, damp environment of pneumatic piping.
Right, and standard PPE just doesn't cut it. They don't ask for a standard N95 paper mask. They specify an FFP3 respirator.
What's the difference?
And the N95 is great for drywall dust, but an FFP3 is rated to filter out ultrafine, hazardous liquid aerosols, and toxic biological growths.
Wow.
If that highly pressurized sludge sprays into your eyes or gets inhaled into your lungs, you are facing a severe, acute medical emergency.
Here's where it gets really interesting, though. Because the stakes are that high, the engineers didn't just rely on written warnings.
No, they didn't.
They mechanically designed the filter housing to actively, physically prevent you from making a lethal mistake. It's like defusing a bomb. The assembly features a specialized safety runner with a locking screw.
Right. It operates as a physical interlock. When the housing is fully threaded together, you must engage this runner and tighten the screw, physically blocking the housing from being rotated.
And the manual is incredibly strict about this. It states the safety runner must visually point forward towards the operator.
It's basically the safety pin on a hand grenade.
You cannot casually walk up to this machine and unscrew the filter body like you're opening a jar of pickles.
No.
The mechanical design forces you to pause, acknowledge the safety runner, grab a tool, and deliberately disengage the lock before you can even begin to apply rotational force.
And the threading on the housing itself is another brilliant example of defensive engineering. It utilizes a double trapezoidal thread profile.
As opposed to normal threads.
Right, standard V-shaped threads concentrate shear stress at a very narrow point, which makes them susceptible to stripping under massive pressure loads.
Okay.
A trapezoidal thread distributes that 232 psi of shear force evenly across a much wider, flatter surface area, making catastrophic structural failure nearly impossible.
Plus, that double thread design allows the housing head to be rotated exactly 180 degrees during installation.
Exactly, so you can pipe the air in from the left or from the right, depending on the layout of your factory.
But the geometry ensures that no matter which way the air flows, that crucial safety runner will always end up facing front and center, highly visible to the technician.
They engineered an ecosystem that anticipates human error. And this raises an important question. How do you design for the real world? The manual includes an entire section dedicated explicitly to foreseeable misuse.
That's such a fascinating concept in industrial design. How do you safely build something when, with absolute certainty that people are going to use it incorrectly?
Right. Foreseeable misuse includes scenarios like operators actively disabling that safety runner because it's inconvenient.
Or failing to wear the mandated PPE.
Or running highly aggressive, unapproved chemical fluids through the system. The designers didn't build this for a pristine laboratory. They engineered it to survive human nature, laziness, and aggressive corner cutting.
But eventually, entropy wins. Even with flawless fluid dynamics, indestructible double trapezoidal threads, and rigorous physical interlocks, the internal filter element is going to die.
It is going to clog.
Yeah. And the back half of the manual provides a meticulous roadmap for how to diagnose the invisible death of the filter and how to safely dispose of the remains.
Preventative maintenance is treated as an absolute law here. On the very top of the external filter head, there is a dedicated, highly visible maintenance sticker.
And the technician is required to physically mark the specific month and year of the next scheduled element exchange.
Yes, the manual dictates an absolute maximum lifespan of 1 year. However, it also provides a strict physical performance metric. The filter element must be replaced the moment the differential pressure gauge registers a drop of 5.8 psi or 0.4 bar.
The physics of differential pressure are really the best diagnostic tool we have for an enclosed system like this, right?
Absolutely. As millions of microscopic dust particles and thick oil droplets slam into that dense borosilicate glass fiber, the microscopic pathways begin to plug up.
It gets physically harder for the compressed air to push its way from the inside out.
Right. So the air pressure on the incoming side of the filter remains at a high 232 psi, but the air pressure on the outgoing, clean side starts to drop because the flow is being choked.
And once the difference between the inlet pressure and the outlet pressure hits exactly 5.8 psi, the system is declaring that the glass matrix is critically choked.
And if a facility manager ignores that differential pressure warning, the consequences are severe.
A blowout.
Yes. The massive force of the incoming air will eventually overcome the structural integrity of the glass and polyurethane. It will physically tear the filter element apart,
Sending a year's worth of accumulated toxic sludge and shattered glass fibers racketing straight into the clean pneumatic machinery downstream. Which brings up a really interesting point in the troubleshooting section. The manual outlines several symptoms of invisible problems. For example, if a facility is experiencing poor compressed quality, meaning dirt and oil are still getting through the manual, suggests a startlingly simple cause.
The internal filter element might just be installed backwards.
Which seems crazy.
Yeah.
But it makes sense because the inside-out airflow defies intuition.
It's a remarkably common error. If an operator installs the cartridge backwards, attempting to push air from the outside in, the coalescing physics completely fail.
The manual also highlights that poor air quality can frequently be traced back to a compromised O-ring seal.
Yes, and they are incredibly specific about the chemistry of those O-rings. You can't just go to a hardware store and buy a standard rubber gasket.
Right. The manual mandates the use of NBR, which is nitrile rubber, or specifically oil-free FKM, which is a highly specialized fluoroelastomer.
The chemical reasoning there is paramount. Standard rubber absorbs synthetic oils. So if you used a normal rubber O-ring, the hot compressor lubricants would cause the rubber to chemically swell, soften, and eventually dissolve into a gummy paste.
And then that 232 psi air would instantly find that weakened path of least resistance.
Blow right past the degraded seal and completely bypass the filter. FKM fluoroelastomers are specifically formulated to remain perfectly rigid and chemically inert even when bathed in hot, toxic hydrocarbons.
Looking further at the troubleshooting guide, there's a remedy suggested for a symptom called high-pressure differential. This means the filter is choking and hitting that 5.8 psi death mark way too fast, maybe in a few weeks instead of a year.
Right.
The manual suggests a solution called stepped filtration. Does stepped filtration just mean putting a filter in front of another filter?
It does, and it reveals the broader systemic philosophy of industrial engineering. You cannot take the H model, the microfilter designed to capture those ethereal zero point 0.1 micrometer particles,
Right.
and install it directly downstream from an old, dirty compressor pushing heavy rust and water.
Because the massive chunks of pipe scale would smash into those delicate glass microfibers and physically pack the cylinder solid in a matter of hours.
Exactly the opposite of efficiency. Industrial purity requires a staged defense against entropy. You must step the filtration down gradually.
Okay, so you start big.
You install the CS course filter first, acting as the brute force vanguard to intercept the heavy pipe scale and large water droplets.
Then what?
Then, further down the line, you install the F-fine filter to strip out the smaller aerosol mists. Only at the very end, right before the sensitive machinery, do you deploy the H microfilter to polish the air and achieve that perfect 99.99% purity.
Each stage protects the one behind it. It's a beautifully logical system.
It is.
But once those filters have done their job, absorbed all that toxic punishment, and finally choked out, the manual makes it very clear that the disposal process is a heavily regulated event.
Oh, absolutely.
You cannot just unscrew the housing and toss the dripping glass cartridge into the municipal dumpster out back.
The environmental impact of that trapped sludge is massive. The manual explicitly dictates that the used filter element must be officially classified and documented under the European Waste Catalog as Waste Code 150203.
That specific code designates adsorption and filter materials that have been heavily contaminated with dangerous, hazardous substances.
Furthermore, the float drain mechanism we discussed, the little mechanical buoy, that must also be processed as hazardous industrial waste.
Because that entire mechanical drain assembly has been marinating in a concentrated stew of toxic synthetic lubricants, heavy metals from the compressor wear, and bacterial sludge.
Which could leach directly into the groundwater if it ended up in a normal landfill.
It's just wild to step back and look at the whole picture. From the microscopic, chaotic fluid dynamics of coalescing borosilicate fibers to the massive, bomb-like physics of 232 psi industrial pressure.
Right down to the strict hazardous waste disposal codes and the FFP3 respirators required just to turn the locking screw.
So what does this all mean?
It serves as a profound reminder that the seamless, functioning, visible world we inhabit is entirely propped up by an astonishing invisible web of hyper-precise engineering, fluid physics, and uncompromising safety regulations.
I want to leave you, the listener, with this image. The next time you are pumping up a bicycle tire or you happen to walk past a manufacturing site and you hear the sudden sharp hiss of a pneumatic valve releasing,
Take a second to picture the intense, completely invisible battles happening inside those dark metal pipes.
picture the microscopic oil droplets violently colliding and merging inside a glass forest.
Picture the little plastic floats bobbing up and down in highly pressurized, toxic chambers, perfectly timing the release of a liquid seal.
And picture the heavy-duty, double-threaded safety runners physically holding back explosive forces, quietly keeping everyone in the building safe.
And, the manual leaves us with one final, lingering implication to consider. If a relatively straightforward device, a threaded metal cylinder that just sits in a pipe and lets air pass through it, demands the staggering level of specialized material science, mechanical fail-safes, specific hazardous waste protocols, and obsessive foreseeable misuse planning.
Fill that up.
Exactly. Imagine the overwhelming, unimaginable complexity of the safety documentation for the larger infrastructural nodes that keep our entire civilization alive. The municipal water treatment plants, the regional power grids, the chemical refineries.
Yeah.
If it takes 50 pages of dense engineering logic to explain how to safely clean the air in a single pipe, who is actively doing the meticulous life or death visual inspections on the massive citywide systems you unknowingly rely on every single second of the day.
It's a slightly terrifying but ultimately awe-inspiring thought. The violent, microscopic, invisible world is the only thing keeping our massive visible world from bursting at the seams. And with that, we'll see you on the next deep dive.